Welcome to the Deep Dive, where we take a stack of information and distill it into the most potent nuggets of knowledge just for you. Today, we're plunging into the fascinating world of superconductivity, specifically type 2 superconductors and this really mind-bending concept known as the vortex lattice. Our sources for this deep dive come from a Nobel lecture given back in 2003 by one of the absolute key figures in this field, Alexei Abrikosov himself.
Yeah, and our mission today, it's really to understand not just the science, which is fascinating enough, but the incredible journey of discovery. The human stories, the surprising turns, and just the sheer perseverance that led to some really profound insights in condensed matter physics. Get ready for some aha moments, I think.
Okay, let's unpack this then. Our story really kicks off back in 1950 with Vitaly Ginzburg and Landau and their famous theory of superconductivity. What was so revolutionary about their approach? What was the big step?
Well, what's really fascinating, I think, is their stroke of genius.
Yeah.
You see, Landau already had this general theory of phase transitions from 1937, and that introduced the idea of an order parameter, basically a variable that's zero above a transition point and not zero below it. For something like ferromagnetism, it's pretty obvious. It's the spontaneous magnetization.
Right, you can measure that directly.
Exactly. But for superconductivity, it was way less clear what that parameter should be. And Ginzburg and Landau, they made this, well, bold choice. They decided to use some kind of wave function as this order parameter.
Huh. And this was before anyone really knew about Cooper pairs or Bose condensates, right? So using a wave function, that was a huge leap of faith, or maybe just brilliant intuition.
Absolutely brilliant intuition, I'd say. And this assumption, it turned out to be crucial. It actually resolved a major contradiction that was sitting there in the older theory by Fritz and Heinz London. That had to do with positive surface energy. And the Ginzburg-Landau approach, it led to a lot of useful predictions too. Things like critical magnetic fields for thin films, critical currents in thin wires. It just laid this beautiful theoretical foundation.
Okay, so the theory seemed elegant, powerful, almost perfect, but then an experiment threw a bit of a wrench in the works, didn't it? Tell us about Nikolai Zavorytsky and his thin films.
Right. Zavorytsky, who was actually Abrikosov's friend and university mate, he started measuring these critical fields of thin superconducting films. And initially, everything looked great. Theory and experiment lined up perfectly.
Ah, the dream scenario.
Yeah, but Zavorytsky's boss, Alexander Sholnikov, he wasn't quite satisfied. He argued the films were probably bad. His reasoning was that because they were prepared at room temperature, the metal atoms might clump together, agglomerate, making the films inhomogeneous, not perfectly smooth.
Okay, that makes sense from an experimental perspective. So Sholnikov advised preparing the films at helium temperature instead to ensure homogeneity. What happened then?
Well, the result was a complete surprise, just total surprise. The new experimental data from these supposedly better films, it just no longer fit the Ginzburg-Landau theory's predictions at all.
Whoa. Okay, so what did Abrikosov and Zavorytsky do? Did they ditch the theory?
No, and this is key. They were convinced the theory itself was sound. I mean, it was elegant, it had worked before, so they looked for a solution within its existing framework.
And that's where this Ginzburg-Landau parameter, kappa, comes in, this dimensionless constant. How did kappa explain the discrepancy?
Exactly. See, for the superconductors, they knew, well, back then, what we now call type by kappa values were very small, like much less than 1. And this small kappa led to that positive surface energy between the normal and superconducting phases we mentioned.
Right, the boundary cost energy.
Yes. And the theory, as it stood, didn't really consider cases where this surface energy could become negative. That seemed, well, contradictory. That didn't fit with the idea of an intermediate state. But Abrikosov, he decided to just push the math. He looked at what would happen if kappa was actually greater than 1 over the square root of 2, that specific value.
The point where surface energy flips negative.
Precisely. He essentially pushed the boundaries of the theory into territory that seemed problematic and found something completely new.
And what happened?
Well, when kappa was greater than 1/2, the whole nature of the transition changed. It became what's called a second-order transition for any thickness. And suddenly, the theory perfectly fit Zavorytsky's new, surprising experimental data. It just snapped into place.
Wow.
And this led them to conclude that there must be this special, different kind of superconductor. They called them superconductors of the second group.
Which we now know as type 2 superconductors.
That's right, type 2.
That is a huge aha moment. And it's amazing to think, like you said, they were considered sort of exotic when Abrikosov published this in a Russian journal in 1954.
Yeah, it took a while to catch on. But if you look at the bigger picture now, wow. Pretty much all the new superconducting compounds discovered since the early 1960s are type 2, organics, A15s, Chevreul phases, heavy fermions, fullerenes, even the high-temperature superconductors.
They're all type 2.
They're all type 2. So
Yeah.
type I superconductors, which were the standard, they're actually the exonic ones now. It completely flipped.
That's incredible. Okay, so with type 2 superconductiles identified, Abrikosov then looked more closely at their magnetic properties, particularly in bulk materials, right? What happens when you put a magnetic field on a type 2 superconductor? It's different from type I, you said.
Yeah, it's very different. So in a type 2 material, the transition to the normal state, when you crank up the magnetic field, it's a second-order transition, like we said. It's gradual. It reaches this upper critical field, Hc2, where superconductivity finally gives way completely. But at smaller magnetic fields, below Hc2, something really unique happens. Instead of just kicking out all the magnetic fields like a type Bi does.
The Meissner effect.
Right, the Meissner effect. Instead of that, the magnetic field can actually partially penetrate the type 2 superconductor.
And this partial penetration, it isn't just sort of seeping in uniformly.
No, not at all. It's
Yeah.
highly structured. Abrikosov's theory showed that the order parameter, that wave function thing, it actually has to vanish, go to zero at specific points. And these points form a regular periodic pattern, like a grid.
Okay.
And around each of these points where the order parameter vanishes, the phase of the order parameter changes by 2p. It sort of winds around that point.
That sounds quite mathematical. What does it physically mean? What does it look like?
Physically, it means the magnetic field isn't spread out evenly. Instead, it gets concentrated into these tiny quantized bundles of magnetic flux. Think of them like microscopic tubes of magnetic field lines. And around each of these flux bundles, a supercurrent circulates, kind of like a little whirlpool, trapping the field inside.
Oh.
And this structure, this localized flux bundle with its circulating current, that's what we call vortex.
A vortex. Okay. And these aren't just random vortices floating around. They form a pattern.
Exactly. They don't just pop up randomly. They arrange themselves into a regular periodic array, a lattice structure. Usually it's a triangular lattice. That configuration has slightly lower energy, at least in simple models, sometimes a square lattice.
Like a crystal, but made of magnetic vortices.
Precisely. And this whole state where the magnetic field is partially inside the material, organized into this pattern of vortices that's known as the mixed state, or, more evocatively, the vortex lattice phase.
And you mentioned quantization. Is this vortex structure linked to that magnetic flux quantum constant?
Yes, absolutely critical point. The amount of magnetic flux passing through one elementary cell of this lattice, essentially, through one vortex, it's a universal constant. It's called the magnetic flux quantum, 10 O0, and it's about 2.05 by 10 cm error. The exact number isn't the main thing, it's that it's quantized. Discrete packets.
A concept from F. London back in 1950, you said?
That's right, London introduced the idea. So as you lower the external magnetic field, the distance between these vortices gets bigger. The lattice spacing increases. Eventually you reach the lower critical field, Hc1. At that point, the vortices are effectively infinitely far apart, meaning the field is entirely expelled. Pure superconductivity, the Meissner state again.
Okay.
And what's really neat is how kappa influences this. As kappa increases, that upper critical field, Hc2, goes way up. The material can handle much stronger fields, but Hc1, the lower field, actually decreases. So the range of magnetic fields where this vortex lattice, this mixed state, exists gets much wider.
Which is hugely important for practical applications like high-field magnets.
Exactly. That's why type 2 is so useful.
So we have this lattice structure. What about the internal structure of a single vortex? What's going on inside one of those flux tubes?
Right, zooming in. So in the microscopic theory, the BCS theory, which sort of underlies Ginzburg-Landau, there are these two really important characteristic lengths. One is the coherence length, symbolized by a Gilliu. That's basically the size of a Cooper pair, the electron pair that carries the supercurrent.
Okay, the size of the superconducting particle.
Sort of, yeah. The other is the penetration depth, lambda. That tells you how far a magnetic field can actually poke into the superconductor before the supercurrents screen it out. And the Ginzburg-Landau parameter, kappa, it's fundamentally just the ratio of these two lengths. Kappa is lambda divided by Gilliu.
Ah, okay.
So for these type 2 superconductors, especially extreme type 2, where kappa is much bigger than 1, it means the penetration depth is much larger than the coherence lengths. Lambda is much bigger than Lea.
So what does that imply for the vortex structure itself?
It means each vortex has this distinct two-part structure. There's a central core region, It's tiny, about the size of the coherence length of the arc. Inside this core, the order parameter, the superconductingness, drops rapidly to 0. The material basically becomes normal right at the very center.
The little normal island.
Kind of, yeah. And surrounding this core is a much larger outer region, extending out to about the size of the penetration depth. In this outer region, the magnetic field, which is concentrated in the core, gradually decays away to 0, and the supercurrent circulates around this core.
And the order parameter has to go to 0 in the middle.
It has to, because the wave function describing the superconductivity has to be single-valued. As it wraps around the vortex core, its phase changes by 2po. The only way for it to be mathematically consistent right at the center point is if its amplitude, the order parameter, actually becomes 0 there. That creates the hole and allows the vortex to exist, and that's where the circulating current is strongest.
Fascinating structure. Now, this whole deep dive, it isn't just about the physics, elegant as it is. There's a really human journey here, too, and a quite poignant story connected to proving this theory right.
There certainly is, and it comes back to that question.
Yeah.
How did Abrikosov even know his theory about type 2 superconductors was right, especially early on? Well, he actually compared his theoretical predictions, specifically how the magnetization should behave in a magnetic field, with experimental results. And these were results obtained by Lev Shubnikov and his team on lead-thallium alloys, way back in 1937.
1937. So Shubnikov had the data potentially showing type 2 behavior long before the theory existed.
Effectively, yes, but it wasn't straightforward for Shubnikov at all.
Yeah.
See, even earlier, around 1935, de Haas and Casimir Jonker had seen this kind of gradual transition from superconducting to normal in alloys, but they just put it down to bad samples. Inhomogeneity.
Right, the easy explanation.
Exactly. So Shubnikov, who'd worked with de Haas, set out to make better samples. He annealed them carefully for a long time. X-rays at room temperature showed they were nice and homogeneous.
Okay, so he thought he'd ruled out inhomogeneity, but he still saw the gradual transition.
He did. He and his group observed it clearly. They had the data, but they just couldn't make the conceptual leap. They couldn't imagine a new phase of superconductivity was appearing.
They were still thinking it must be some kind of hidden inhomogeneity.
That's what they figured. They thought maybe some other phase was precipitating out, like tiny impurities forming, only at the lower cryogenic temperatures. That was their explanation for the mixed behaviors.
The truly tragic part.
The truly tragic part is what happened next. Lev Shubnikov was accused of organizing an anti-Soviet strike. He was arraigned by the KGB and executed in the very same year, 1937.
Oh my God.
Abrikosov, in his Nobel lecture, pays this really profound tribute. He says he was absolutely sure Shubnikov would have figured out type 2 superconductors if he just had the chance. And he explicitly states that Shubnikov's data provided real inspiration for his own theoretical work years later. It's a stark reminder of the human element in science.
What an absolutely incredible and tragic story. And even for Abrikosov, getting his own work on the vortex lattice published wasn't smooth sailing, even with Shubnikov's data as inspiration.
No, indeed. He actually derived the vortex lattice structure back in 1953. But its publication got held up.
Why?
Because Lev Landau, his mentor, incredibly influential physicist, Landau initially just didn't agree with the whole idea. He couldn't accept this kind of ordered vortex structure within a superconductor.
Really? Even Landau?
Even Landau. It was only after Richard Feynman published his paper on vortices in superfluid helium, which is conceptually similar phenomenon in a different system, in 1955. Only then did Landau apparently accept the general possibility of vortices, and Abrikosov's paper was finally allowed to be published in 1957.
Wow, a 4-year delay just because of initial disagreement. And even then, when it was published, it didn't immediately set the world on fire.
No, not really, not at first. Even though there was an English translation available pretty quickly, it really wasn't until the early 1960s when experimentalists started discovering all these new superconducting alloys and compounds, materials that had really high critical magnetic fields.
Type 2 materials.
Exactly. That's when interest in Abrikosov's 1957 paper suddenly surged. But even then, there was skepticism. A lot of experimentalists still found it hard to believe in this perfect vortex lattice, especially one that wasn't lined up, wasn't commensurable with the actual crystal lattice of the atoms in the material.
Right. It seemed weirdly independent. So when did they finally get undeniable proof? When did people have to believe it?
The definitive proof came when they could actually see it, or detect its structure directly. First was neutron diffraction in 1964. Neutrons can sense magnetic fields, so they could detect the regular pattern of the vortex magnetic fields.
Okay, indirect imaging.
Right. And then, maybe even more convincingly, in 1967 came a visual technique called decoration. They basically sprinkled tiny magnetic particles onto the surface of the superconductor in the mixed state. And these particles naturally got attracted to and stuck on the vortex cores where the field is strongest.
So they literally decorated the lattice pattern.
Exactly. You could see the pattern under a microscope. Today, of course, we have much fancier techniques, electron holography, scanning, tunneling microscopy that can image these vortex lattices beautifully. But it really is a testament to Abrikosov's theoretical insight and perseverance against that initial wave of skepticism.
Absolutely. Now, the vortex lattice is clearly a monumental achievement. But Abrikosov's Nobel lecture, it also touches on other areas he worked on in superconductivity, right? It wasn't his only contribution.
Oh, definitely not. Superconductivity was clearly his favorite field, he said so himself, even though he worked on tons of other things in physics. In the early 60s, for example, he worked closely with Lev Gorkov, really extending the microscopic BCS theory. They looked into tricky things, like how superconductors behave in high-frequency fields, or what happens when you add magnetic impurities.
Magnetic impurities sound like trouble for superconductors.
They usually are. But studying them led Abrikosov and Gorkov to discover something called gapeless superconductivity, where that energy gap, which is normally essential for zero resistance, can effectively disappear under certain conditions, yet the material can still superconduct in some ways.
Huh. Counterintuitive.
Very.
Yeah.
And they also solved a long-standing puzzle about something called the night shift at low temperatures by introducing the idea of spin orbit, scattering how an electron's spin interacts with its motion.
So deep dives into the fundamental mechanisms. And he even took on the big one, the quote-unquote mystery of high-temperature superconductivity later on.
Yes, he did. After Bednorz and Mueller made their Nobel-winning discovery in '86, finding superconductivity at much higher temperatures in these layered copper oxides, well, the theoretical world kind of exploded. Lots of really exotic mechanisms were proposed.
Right. People thought it had to be something completely new.
Abrikosov's approach was different. He basically said, let's start with the established BCS theory, but let's be really careful to incorporate the specific features of these new materials. Things like their quasi-two-dimensional nature, the fact they're layered, specific features in their electron energy bands, these flat regions, and also something called resonant tunneling between the copper oxide layers.
So modifying BCS rather than throwing it out?
Exactly. And he argued quite forcefully that by doing this, by carefully accounting for the real material properties within a sort of extended BCS framework, he could explain most of the experimental data. He didn't think you needed fundamentally new physics or needed to divide materials into good ones that fit theory and bad ones that didn't. He rather controversially stated, essentially, that the mystery of high TC superconductivity does not exist.
Bold statement. Okay, what an incredible journey we've really taken today. From that brilliant, intuitive leap by Ginzburg and Landau through the experimental surprises that Zavorytsky uncovered, leading to Abrikosov's groundbreaking insight that revealed type 2 superconductors, and then this beautiful, complex order of the vortex lattice.
It really is a profound reminder, isn't it, that scientific progress, it's just not a straight line. It's messy, is full of unexpected data, puzzles in the theory, plenty of initial skepticism, and these deeply human stories of perseverance, flashes of inspiration, and even, sadly, tragedy, like we saw with Shubnikov. And that act of pushing boundaries, like Abrikosov did with Kappa, just asking, what if? That's often what reveals entirely new scientific landscapes.
It absolutely highlights how an initial theory, even a stroke of genius, gets refined, gets challenged by experiments, and then gets expanded. And in expanding, it reveals whole new realms of understanding that, ultimately change how we see the world and what technologies become possible. Paying attention to the anomalies seems key.
So what's the takeaway here for you listening? Maybe consider how pursuing knowledge, even when it seems a bit exotic at first or seems to contradict what everyone knows, how that pursuit can uncover truly universal principles and lead to technologies we couldn't even imagine before. This deep dive into superconductivity, it leaves us with maybe a provocative thought to chew on. How many other mysteries out there in science or elsewhere are just waiting for someone to look just a little bit deeper, maybe re-examine data we think we understand, but with fresh eyes, with that willingness to challenge assumptions, maybe revealing elegance and order where right now we only see contradiction or confusion.
A fantastic thought to end on. Until next time, keep exploring, keep questioning, and keep diving deep.